So my project was on coronal mass ejections, specifically kinematics, studying plasma velocity and acceleration. So my mentors were Diana Besley Ionescu and Marilena Mierla from the Astronomical Institute of the Romanian Academy. So my presentation is structured pretty much the same way that my research project was. I'm going to start with an introduction where I just define like specific terms that are important to know and just what a CME is in general. And then I talk about the methods that I use for my research project, how I gathered data on kinematics, focusing on velocity and acceleration. And then I present my results in the form of like my graphs and the data and how that compared to existing data on CMEs. And then I discuss my findings, talk about how it's important, and then I have my conclusion and my references. So, starting off with just what is a coronal mass ejection? It is an ejection of plasma from the sun's corona, which you can see here in this picture on the left. And it's often confused for a solar flare. The two solar events are pretty similar and they often occur together, but they're not necessarily the same thing. Um, a CME is an actual ejection of plasma and particles, energized particles like electrons, beyond the sun's corona into the heliosphere, whereas a solar flare is mostly an ejection of particles. There's no like physical matter being ejected from the sun in that instance. And CMEs have a tendency to spread their particles a lot further than a solar flare would. So CMEs occur under high stress in the sun's magnetic field. um, this is because magnetic line reconfiguration occurs whenever the sun's magnetic lines are under too much stress. And when this reconfiguration occurs and the excess energy is dispelled, it emerges from the sun in the form of a CME, specifically in the form of like a flux rope, which then leaves the sun's corona in like the shape of a loop, which you can kind of see here. It's like a loop shape. And these highly magnetized areas in the sun's corona are called sunspots. So CMEs mostly occur nearby sunspots. The electrons that are released in CMEs have a major impact on like the solar wind. It causes disruptions depending on the size of the CME and the geomagnetic field surrounding the Earth. It affects that too. And the movement of high energy electrons caused by plasma shock also cause radio bursts, which are another way that CMEs can affect the geomagnetic field around Earth. And the intensity of these plasma shocks depend on the CME's velocity and acceleration. So starting off with the research objective, I'm using coronagraph images from LASCO, which stands for Large Angle and Spectrometric Coronagraph Experiment, aboard the SOHO, which stands for Solar and Heliospheric Observatory mission from NASA. So that's a mission that's in space currently and is constantly taking pictures in the form of coronagraphs of the sun. So because you can't actually photograph the sun, the way a coronagraph works is it captures the light and the electrons that are emitted from the sun during events such as these. So as you can see, it kind of shows up as a white image because that's just light from the CME. So my objective was to manually collect data on kinematic parameters of CMEs, specifically velocity and acceleration, by tracking it through these images of coronagraphs that I have via JHelioViewer, which is a program. And then I was going to observe specific and minor details in CME evolution that a catalog such as the CDA database that already contains CME data might not contain because it assesses the entire event rather than specific points in the event. Then I would cross-check my own data, all the calculations that I made against the CDA database to see if there's any inconsistencies or similarities between my computed data and the catalog's data. So starting off with my methods, I selected two CMEs. The first one was on April 20th, 1998. This one I selected because it's known to be a especially fast CME, like it's record-breaking for its velocity and acceleration and how fast it traveled. It was a pretty big event. And the second one that I selected was December 9th, 2002. This one I selected because it was only within 4 years of the previous CME that I selected, so the change in technology wouldn't have been too great, so there wouldn't be an inconsistency with my calculation. And also because this CME was very distinct, it was very clear, so I didn't have a hard time plotting points. So what I did was I selected 5 frames of images from each of these CMEs that tracked its progression as it propagated through the heliosphere. And what I did was I plotted a point at the furthest part of the CME front from the sun for each frame, which you can kind of see in the picture I have on top. I drew a line that followed the path of motion for the CME. And then for each frame, I plotted a point at the very front of the CME just to show how far it had spread during that time frame. And all data collection that I had done was through the computer program JHelioViewer, which imports data from Soho Lasco. So once I'd collected all the data points, all 5 data points from each of the CMEs, the first thing I did was using the heliocentric radius that they gave me, I converted that by a factor of 1 radian subradius equals 695,700 kilometers, because I wanted my final calculation to be in kilometers per second for velocity and kilometers per second squared for acceleration. So once I had done that, I then used the timestamp for each of the points that I plotted and did the math so that it would come off as time since I started recording the CME. And then what I did was I put both of them into a position versus time graph so I could get a rough estimate of its path of travel through the sky. After graphing it, the next thing I did was I followed 2 main methods to determine the velocity and acceleration. The first one was based on the graphs. I used the midpoint approximation formula to get the velocity, and then using my midpoint approximation of velocity for each point, I also made an approximation of acceleration using the formula here. The second method that I used was a line of best fit, which is visible in the previous slide. I used a line of best fit that was a polynomial to the 4th degree. It's visible right here. This equation would represent my velocity, and what I would do is plug in a certain variable for t to find the velocity at that point. And then to get acceleration, I took the derivative of that equation and repeated the steps. I plugged in the time for each of them to get a slightly more accurate variable for acceleration. Once I'd done that, what I did was I compared the calculations that I had made, both the approximation and the derivative calculation, to the CDAW database, which is the official database for Soho Lasco information. And I tried to identify any similarities or differences between my calculations and the official data on the website. So my findings, most of my calculations, actually all of my calculations, were within the normal ranges for velocity and acceleration or CMEs. So for my 2002 CME, the velocity at each point was somewhere within the range of 600 to 800 kilometers per second, and 800 to 1600 for the 1998 CME, because as I mentioned previously, that coronal mass ejection was significantly faster than the average. And one of the main differences between my calculations and what I found on the online database was that the acceleration I got for the 1998 CME was significantly smaller than the CDAW database. As you can see here, both my midpoint acceleration and the derivative average that I got were pretty small numbers. This one's negative. And then the acceleration in the database was 43.5 meters per second squared, which is a pretty big difference. So the likely reason for this is because the database captured velocity of this CME over a longer time frame. I was only using 5 frames of this solar event. And because of how fast it was moving, I didn't have a very clear picture because for every single frame, the plasma traveled very far and dispersed. So by the time I got to the 4th and 5th frame, I was kind of making a very rough estimate of where the CME front ended. This happened again because 1998 CME had a record-breaking velocity. The 2002 CME is a lot more accurate in my calculations just because I had so many more frames to work with and because it wasn't as fast moving. So, continue with my findings. There are some pros and cons to the method that I chose to use. Graphing data on velocity and acceleration manually meant that I was able to interpret the speed and velocity at a much smaller level because I was calculating velocity and acceleration for each point in its path of motion. as opposed to what the CI database does, where it calculates its average acceleration and velocity over its entire path of travel, which is a lot larger than what I was doing. My method lets me see certain things that you wouldn't just get from the database because, for example, the 2002 CME actually experienced some deceleration before accelerating again, which can indicate a lot of things. You can make a lot of inferences. For example, it might have slowed down because it faced interference in the solar wind, or it slowed down because of its mass, and then it might have lost the mass as it continued in its path of travel. You wouldn't be able to find something like that through the database alone. And then another reason that manual graphing was really important is because the high speeds of the 1998 CME would indicate that it had a large geomagnetic impact. So what I can do is I can use the data that I found, with my kinematic parameters, and then compare that to the geomagnetic effect of these solar events and find a correlation between the kinematics, the speed and the acceleration, and how they impacted the Earth's geomagnetosphere. Some problems with my method though, the main one being that 2D graphing doesn't account for out of plane motion. Coronal mass ejections are a three-dimensional event. However, I'm looking at a 2D picture and graphing it in 2 dimensions. So the data isn't as accurate as it could be. And additionally, as I mentioned previously, because I'm graphing these by hand, if the CME front gets really faint, like what happened with 1998 CME, it might be difficult to distinguish where I'm going to plot my point to represent distance. So in my conclusion, I thought about some improvements to methods, and one of the main ones would be using 3D graphing instead. More recently, NASA launched the STEREO mission, which stands for Solar Terrestrial Relations Observatory. And on that mission is the IMPACT tool, which stands for in situ measurements of particles and CME transients. And what this does is, unlike LASCO, which only has one viewpoint, IMPACT has two different viewpoints. So you're viewing the sun from two different locations. And while these viewpoints give you a two-dimensional view, you can combine the data from each of these to estimate a 3D model of a CME, which gives you a lot more information about its plane of motion and its path of propagation throughout the heliosphere. And although this isn't a completely accurate model, this is significantly better than 2D modeling just because it gives you so much information about how the energy of the CME is traveling. Some other improvements I would make if I were to run this research again is if I were manually graphing more CMEs, I would try to use more frames, maybe like 10 instead of 5, over a wider span of time so I can gather some more accurate data. Lastly, I just want to talk about why I'm studying CME kinematics. I mentioned before that the kinematics, such as speed and velocity, have a major impact on how much the CME can affect the geomagnetosphere. Um, Especially because fast CMEs are likely to drive shock waves and trigger geomagnetic storms, and these can disrupt satellites, or GPS power grids, radio communication systems, things like that, anything that travels in radio waves. One such example was in February of 2022, where a particularly powerful CME occurred that caused a geomagnetic storm around Earth. And because of that, 38 Starlink satellites were lost just because of how powerful the interference was. So yeah, by analyzing CME motion, we can improve models of how these eruptions propagate through the heliosphere and interact with solar wind and other energy that exists in our solar system. And this helps us to make better predictions in the future about space weather, which can help us protect our technology and also communication systems in space. Lastly, I just want to do my reflection and acknowledgement. A big thank you to Talaria for the opportunity to conduct this research, as well as to my mentors for their support and guidance. Even with the major time difference, we were able to communicate, and I just learned a lot about how I'm collecting data for research and how to write a research paper. And I especially enjoyed the math and graphing because it was really interesting to see how close my calculations got to actual recorded data, when all I was using was images that I could find online or through a program. So these are my references, and that concludes my presentation. Thank you so much.